All right, so we're back. We're talking now about the, the different characteristics within streams. So we're going to talk about pools and riffles. So a pool, probably something you've seen before, a deep, slow-moving section of the stream. A riffle, though, is an area where you have cobbles and the water kind of moves turbulently through on top of the cobbles and sometimes through the cobbles. So we talk about a section of a river as one that has multiple pools and riffles within a reach. So when you go out to your field sites, find a stream segment that has multiple pools and riffles, hopefully. In general, we call a reach 20 times the width of the stream, or sorry, yeah, 20 times the width of the stream is a reach. What's neat is about pools and riffles is that you can see a picture from the side at first showing the riffle and then the pool and the riffle and the pool. And the velocity of the riffle often causes the digging out of the pool, and then the pool itself causes sediment to drop in the bottom. And so these riffles and pools migrate throughout the river over time. So they're not static features. They don't stay in one place. The other thing that's really cool is if you look at the top, from the top, like from the sky, and you look down, you'll find pools tend to be on the outside edge of a turn, and then you have a bar building up on the inside edge of a turn, and then you have a riffle that connects the next pool, which is on the outside edge of the other turn. And so depending on whether you have really strong curvature, sinuosity in your stream or not, you're still going to have this pool, riffle, pool structure. And it should be pretty predictable where you'd find a deep spot and where you'd find a gravel bar, where you find a riffle, things like that. And the dotted line that you see in both figures is called the thalweg, or the place of fastest flow or deepest flow. And so you can also kind of track the thalweg, and you can see it scouring out the outside of each bend, and that's called a cut bank. And then it's dropping its load on the bar on the inside of each bend. So these are really cool repeating patterns in streams. Here you can see a bunch of different features. You have at the top things like cascades, waterfalls, plunge pools. You have deep pools and shallow pools. You can see what it looks like on the side of a cascade in the profile. You can see a pour over. You can see some rapids and riffles and what they look like from the side. You can see a lateral scour pool on the outside of a bend. Over here, you can see what's called an oxbow lake. I'll get to that in a minute, but it's basically an old outside bend. And then you can see what a glide or a run both look like. So lots of really cool kind of features to see what they look like from the side profiles as well. So riffle to riffle distance, if you were to measure it, it's kind of like a wavelength, what you learned about sine curves. The riffle to riffle distance tends to equal about 5 to 7 channel widths. So this will be interesting when you pick your stream sites, whether this is true. Okay, so even in a straight stream or in a sinuous stream, you should get the same patterns. So I keep using this word sinuous. It basically means how meandering, how bendy is the stream. Okay, so you can have the stream kind of flowing in a straight channel, or you can have the stream starting to flow in a sinuous channel. And when sinuosity gets really extreme, we call it meandering. You can calculate the sinuosity ratio, and you'll have a chance to do this. So you go at the top of your reach and you go to the bottom of your reach and you measure the straight line distance between the two. And then you walk down the stream, finding the thalweg, that deepest flow, and you put pin flags as you go. And then you take a piece of string and you wrap it around each pin flag to measure the sinuous distance between A and B. And say your straight line distance is 50 meters and the sinuous distance that you measure is 80 meters, then you calculate the sinuosity ratio by taking the the distance between the 2 points measured along the stream divided by the straight line distance between the 2 points. So 80 meters divided by 50 meters. Looks like the meters both cancel out. So the sinuosity ratio is a unitless measure. And in this case, we get a sinuosity measure or sinuosity ratio of 1.6. Okay, so that's how you calculate sinuosity. Now, when sinuosity gets really extreme, we get what are called meanders. And typically one meander wavelength ends up being about 11 times the river width. So if you're wondering if your stream is meandering or not, then this is a good guide. Also, the radius of the curve ends up being about 1/5 of the wavelength. These measurements come from Luna Leopold, who was a groundbreaking hydrologist in the mid 20th century. And typically, a river is considering meandering if it has a sinuosity ratio of greater than 1.3. So here's pictures, lots of really cool pictures of meanders. So here's another meandering stream in its floodplain. You can see what are called meander scars, which is where the river may have been in say a flood, possibly, or an oxbow lake, which is where a meandering arm got cut off. You can see in the middle here. This arm might have used to gone like this, and then at some point it got cut off, leaving behind what's called an oxbow lake. That's also called a billabong if you're in Australia. And yeah, so really cool meander scars will show you where a river has been and how dynamic rivers are. So here you can see a picture showing some meander scars and the development of an oxbow lake. This is showing you how meanders form. Again, the cut bank has erosion taking place and then deposition on the inside and then more erosion. So meanders generally become more pronounced until the arms get cut off and then they get more streamlined. Here's some really cool pictures from Brazil, just taken from Google Earth. And you can see some really neat old meander scars and oxbow lakes all around. This is Carajuari in the state of Amazonas in Brazil. Looking a little bit closer, you can see these really neat patterns just from space. So it's really fun to just play around in Google Earth. And this is a picture from the Willamette River in Oregon using LiDAR. So right now, the floodplain in the Willamette River is completely farmed. It's covered with agriculture. And so if you were to look at this, all you would see is the stream with some trees growing alongside. But if you use what's called LiDAR, which is light detection and ranging, then you can see through those crops to the meander scars and the geology underlying. And so it's really, really impressive to see where the Willamette River has been and really where it should be given room to roam, right? Like this is what rivers do. And instead we build things all along them and expect them to stay put. And that's just really not something that rivers are meant to do. So what you're seeing here in the lowest elevation is white. So that's the kind of the main stem. And then the fluvial zone is where the flowing channel is. So the really white parts. The parafluvial zone is where we see regular floods. And so some of the kind of mistier, shadier spots. And then the orthofluvial is the whole floodplain. And this whole image is in the floodplain. This is from the Oregon Department of Geology and Mineral Industries, and a person named Daniel Coe put it together. And you can buy this as like a really cool poster if you want online. Okay, I'm going to talk about slope. So I'm actually going to have you take a break, and then I'm going to come back and have you talk about slope because we're going to get into some trigonometry. So take a little break, and we'll come back.